Section 6.5, Work. Another application of integration involves calculating work done in the presence of a variable force. Recall from basic physics that work equals force times distance, but this formula from basic physics applies when the force here is constant. Now before we move on to a variable force, let's just do a units review. Remember that in SI units, force is in newtons, which we denote by a capital N. 1 newton is defined to be 1 kilogram meter per second squared. And work is in joules, we denote by a capital J, and 1 joule is 1 newton meter. In the British system, force is in pounds, denoted by lb, and work is in foot-pounds, denoted by this. So example 1, find the work required to move a 2 kilogram rock 3 meters above the ground. Now this doesn't require any calculus because the force here is constant, but work is force times distance, and the force here is just the force required to overcome gravity acting on the mass. So force is mass times acceleration. Our mass was 2 kilograms. Gravitational constant here is 9.8 meters per second squared, and the distance that we're moving the rock is 3 meters. When we multiply this out, we get 58.8, and the units coincide with Newton meters, or 58.8 joules. As a second example, let's calculate the work required to lift a 2-pound rock 3 feet off the ground. So notice we are using British units. Now again, work is force times distance, and the force here is the weight of the rock. Notice in the British system, we have that weight is measured in pounds, which is already a force, and so it has gravitational acceleration built into it. So this is simpler in a certain sense. The force is just 2 pounds, the distance is 3 feet, so the total work required to move the rock is 6 foot-pounds. Okay, but where does calculus come in? Well, it happens when the force here is not necessarily constant. So suppose F is a variable force, and it varies over the distance over which we're performing the work. Then work is defined as the integral from a to b of f of x dx. So it's just the work required. We integrate the force over our interval to get the total work required to overcome that force. You could think of it as an accumulation of work done as the force varies over the interval, the x interval from a to b. A classic example of this would be a spring mass system. So if you think of a mass on the end of a spring, and let's just say that it's at its equilibrium position, if you wanted to grab this mass and stretch the spring, then the spring is going to resist that stretching, and depending on how stiff it is, that resistance could be quite a lot. And similarly, if you went to compress the spring, then when you compress the spring is going to resist it being compressed from its equilibrium position. And Hooke's law from basic physics says that the restorative force from the spring is directly proportional to, but in the opposite direction of the displacement. And this constant K, this proportionality constant, is called the spring stiffness constant. So a really stiff spring would have a large K, a very loose spring would have a small k. And we call this the restorative force because it works in both directions. If you're stretching the spring, the restorative force would be wanting it to return backwards to its equilibrium position, whereas if you compress the spring, then the restorative force would be working to the right in order for the spring to go back to its equilibrium position. And we know this from everyday life, having, say, played with a slinky before. Now the work to stretch the spring, notice the force is not constant. The further you stretch the spring, the more force that the spring is exerting against you to try to restore back to its equilibrium position. So this is a classic example of a variable force. So suppose we want to calculate the work to stretch the spring, say from its equilibrium position, to a point that is a units we're stretching. So here a is positive, where we're stretching it to the right. Then this would just be, following this formula, the integral from 0 to a of k times x dx. Notice that the force that we're acting against is we're acting against this force, so it's in the opposite direction, so we do not have a minus here. This is how the spring is acting on to restore the spring to its equilibrium position, but the force we're overcoming is working against that force, and that's why we do not have the minus sign here. Similarly, if we wanted to compress the spring from, say, x equals 0 to x equal b, where b is less than 0, then we would be compressing the spring to the left in this diagram, And now we would be integrating our force function, again it's positive not negative, from 0 to b, where we can write this as either write it with b where b is known to be negative, or we could write it as a negative b where b is written as positive. Here I write it as with a negative b where b is positive. Notice if you look at both the geometry and the calculation of that integral, the spring stiffness constant itself is always positive. Then the work here comes out to be positive just as it should be. And that's because notice that even though when we look at this function that we are integrating from 0 to minus b, so we were integrating from right to left, opposite of what we normally do. But the work here is positive. So as an example, consider a spring that has a spring constant of 400 Newton meters. We'll just tell you that. The first question is how much work is required to stretch the spring 10 centimeters beyond its equilibrium position? And secondly, how much work is required to compress the spring 2 more centimeters when it has already been compressed 3 centimeters from its equilibrium position? Okay, so for the first, we can just visualize a diagram. Here we'll show the spring in its equilibrium position. We want to stretch the spring, so we'll move it out to the right. We want to stretch it 10 centimeters. Hooke's law tells us the force that we need to the restorative force due to the spring is minus k times x, so the force we have to overcome is just k times x. Our k here is 400. And notice that for our units to be consistent, that our x needs to be measured in meters, so we will rewrite 10 centimeters as 0.1 meters. And so work is the integral from a to b of f of x dx. We would integrate from 0 to 0.1, 400x dx. That's a very basic integral to calculate. It comes out to be 2, and the units here are joules. This is positive work, just as we would expect it should be. Okay, on the other hand, suppose that we have a spring in its equilibrium position, and before we even arrive at the situation, it's already been compressed 3 centimeters from its equilibrium position, so 3 centimeters to the left, and that's where the situation stands. And now we want to come along and we want to compress it 2 centimeters further to the left. We're not trying to calculate all of this work, just the work to move it from the 3 centimeters left position to the 5 centimeters left position. Again, work is the integral from a to b of f of x dx. We've already said that our force is 400x. And now it's just a matter of integrating from the 3 centimeter left position to the 5 centimeter left position. We do have to keep in mind that our units have to be consistent, so we're going to rewrite 3 centimeters to the left as negative 0.03 meters and write 5 centimeters to the left as negative 0.05 meters. And now we would integrate from minus 0.03 to minus 0.05. Once again, we're integrating from right to left of 400x dx. This comes out to be a positive 0.32 joules. It's positive work just as it should be. Here's a different type of example. Suppose that you have a hose and it weighs 1/2 pound per foot of length of the hose. Find the total work done in reeling all of the hose in. So if you're going to pull the hose in by hand, what is the total amount of work that you're going to do? And of course, we're not moving the entire, every time we reel in some hose, the hose is getting shorter. And so we're pulling less weight with every pull. So the force here, due to the way the hose is not constant, but it rather varies depending on how much hose we've already reeled in. So as a simplistic diagram, think of it like this. We have 100 total feet of hose. Let's act like we've already reeled in x of it, where x is going to change. We have 100 minus x that's left to be reeled in. And so the force that we have to deal with here is just the weight of the length that is yet to be reeled in. So if we've yet to have reeled in 100 minus x feet of hose, and we know that it weighs 1/2 pound per foot, then we just calculate the force as the weight, which is just the length to be reeled in, times the weight per unit length. We multiply these two, we get 50 minus 1/2 x. This is our variable force function. So our work is the integral from what is the smallest amount of hose that could be reeled in to begin with is 0. What's the largest amount of hose that has to be reeled in? Out to the 100th foot. And of our force function dx, it's a very straightforward integral to compute. It comes out to be 2,500. And the units here in British system are foot-pounds. Next, let's look at an example where we compute the work required to pump a fluid out of a tank. So suppose we have a conical tank with a base radius of 3 meters and a height of 12 meters, and the tank is full of water. We want to calculate the total work required to pump all of the water out of a spout that sits 1 meter above the top of the tank. Note that the density of water is about 1,000 kilograms per cubic meter. So much like our earlier work in Chapter 6, we want to draw a nice diagram. We want to label the relevant dimensions. And so here we have a base radius of 3. The conical tank has a height of 12. We have a spout that sits 1 meter above the top of the tank. And the idea is that we want to take an infinitesimally thin slice of water, and we want to calculate the work required to move that slice of water to the desired location. Okay, so let's coordinatize things by just taking a cross-section, a vertical cross-section here, and we turn this three-dimensional picture into this two-dimensional picture. And once we do that, we see the base radius of the tank here is 3. We see the height of the tank is 12. We see that our slice height of water is y. We also see that the spout sits 1 meter above the top of the tank. So if this distance is y, then this distance would be 12 minus y, and this distance would be 13 minus y. Okay, I think we have everything that we need in this two-dimensional diagram. So now let's work on calculating the work required to move that one slice of water from here to the top of the spout. Well, work is force times distance. Force is mass times acceleration. And here this is just the distance that we have to move that slice of water. And notice different slices of water will need to be moved different heights. Okay, so force is mg. The distance here is d. And now recall that density is mass per unit volume, which we can rewrite this. We've already used the letter d, so it's very common for density to use the Greek letter rho. So rho, that's not a p, but a rho. Rho is mass per unit volume. Density is mass per unit volume, which we can cross-multiply and rewrite as mass is density times volume. Okay, so now we can come back and rewrite mass as density times volume. And when we talk about volume, we're talking about the volume of this particular slice. We still have g, and we still have our vertical distance d that we have to move the slice through. So let's go off to the side here. Density is a number that we know. They told us in the statement of the problem that the density of water is about 1,000 kilograms per cubic meter. So we will just leave that as a constant rho for right now. And then we also know g, and here since we're using SI units, we have 9.8 meters per second squared. So this is just a constant, this is just a constant. We really need to concentrate on this and this. So why don't we tackle this first? So just like earlier in Chapter 6, if we go up here and we look at this slice of water, when we've sliced things in this direction, we get that the volume of the slice is just the area of the face times the thickness, but a slice here is just a tiny, infinitesimally thin cylinder. So the area of the face is just the area of the circular face, so it's pi times the radius squared, where the radius is the radius of that slice, times the thickness, which is a thickness in the y direction. Now, if we look back at this diagram, we see that the radius of our slice is really this x value. This x value depends on this y value. So once we fix a slice height and y is fixed, that will dictate x. All right. So really the radius here depends is x, and it varies as y varies, and we really need to know x as a function of y. We need to know how x changes as y changes, because we can see by reading our keys here in our work that our delta y here where it tells us that we're eventually going to be integrating with respect to y. So I need to write x as a function of y. But we've done this before. We can use similar triangles, and we see that this triangle here is similar to this triangle here. And so we could set up a variety of proportions here. The one that I did is I just said 3 is to x as 12 is to y. And when you do this and you solve for x in terms of y, we get that x is 1/4 y. So I'll just replace x with 1/4 y. It's still squared. If we simplify this, we get pi over 16 y squared delta y. And that is the volume of our slice. So let's take this. Let's put it back in where we had the volume of the slice, pi over 16 times y squared, delta y. We still have the g, and then the vertical distance that we need to move that slice through. Well, if our slice was sitting here, we need to move it this distance. And when we had a slice height of y, our distance that we need to move it through, in this case, is 13 minus y. So we'll put that in for our distance. Vertical distance is 13 minus y when we're at a slice of y. And we're just about done. We've done as much as we can do with this. And so now we're ready to accumulate all of the work on all of the slices. So the total work will just be integrating this. And we'll go ahead and pull out the rho, the g, the pi, and the 16. And that's going to leave us with an integrand that is y squared times 13 minus y dy. And now we see that the limits of our integration, our slice heights, that's what y stood for, could be as low as 0, and our slice heights could be as high as 12. They don't go above 12. This is the distance that we're going to move our slice through, but our slice heights themselves could be as low as 0 and as high as 12. So here we're going to integrate from 0 to 12 after we pulled out the constants of y squared times 13 minus y. And I like to do this way, just leave these as constants and then plug them in at the very end. It's a little less writing. Our rho, our density of water, and it wouldn't matter as long as we knew the fluid density. We could pump whatever fluid you wanted to here. But here they tell us that the density of water is 1,000 kilograms per cubic meter. We know that g is 9.8 meters per second squared. Pi is just a constant, 16 is a constant. This is a very straightforward integral to do. You just multiply through and apply the power rule. And so when the calculus dust settles, this comes out to be about 4.43 times 10 to the 6 joules is the total amount of work needed to pump all of the fluid in this conical tank through a spout that's 1 meter above the top of the tank.